This is a book summary of Chance by Amir Aczel, 2005. The introduction begins with looking at the ancient history of probability. He mentions that the Greeks had Tyche, a goddess of fortune, and the Romans had Fortuna. Claudius wrote a book about Roman dice games around AD 30. Dice were used by tribes in prehistory. There's evidence of Roman, Jewish and Indian expertise in probability and statistics, including far-out statistics. The ancient Greeks, including Euclid, lacked an interest in probability. The occult and divination used chance. Modern probability is very much about the Europeans in the 17th century. It was a very interesting collaboration between a gambler called Ch1 and two very famous mathematicians, Blaise Pascal and Pierre de Fermat. Moving on to chapter 1. Some of these chapters are very concise and profound. In chapter 1, he introduces the probability scale from 0.00, which would be impossible, to 1.00, which would be absolutely certain. And most probabilities will be expressed on this scale, such as 0.19 or 0.64. You can quite easily convert those probabilities on that scale into a percentage. So 0.55 would be 55%, and so on. Moving straight on to chapter 2, he says here that probability, measuring probability, is really as simple as counting. What you do is you count up all of the possibilities of an event happening, and you divide that by the total possibilities. At the end of this chapter, he also introduces a type of probability card, which is used for card games. So it has columns going down: ace, king, queen, jack, 10, 9, 8, and so on. And there are 4 columns for the 4 suits of cards. Moving on to chapter 3, here in probability. Now, the oral we probably remember from GCSE maths, the probability of A or B happening. To find that out, we take the sum of probability of A and B, the product of probability A and B. The reason for the subtraction is that a little bit of it would have been counted twice if there wasn't the subtraction. He also introduces in this chapter Venn diagrams, the union and the intersection. I won't be talking very much about Venn diagrams because I think that probability trees are better, because probability trees can show developments over time and Venn diagrams cannot. Moving on to chapter 4, here this chapter is mostly about all of those classic problems where it's either with replacement or without replacement. Now, if it's without replacement, then the second step on your probability tree is going to be out of 1 less than at the first step. So we tend to get these calculations like 5/10 from the first stage of the probability tree times 4/9 at the second one, if you're trying to work out the probabilities. He also introduces a sample space diagram, which is pretty much just like a grid, and that's for rolling 2 dice at once. And if you use that, it's a bit like a sort of times table chart. Then you'll see lots of 7s because when you roll 2 dice, there are lots of ways to roll 7, and very few ways, for example, of getting, well, only one way of getting 12, and only one way of getting 2. Okay, so he also says that blackjack has an unknown sample space due to casinos using many decks of cards. Moving on now to chapter 5. This chapter's about subjective probability. It's sort of about applying balls in the bag probability, 80 red balls, 20 black balls, to real life events. So he starts off, one of his first examples is the chance of a rainy day in July, and he calculates this as 6 out of 93, 6 over 93. And this is based on data from several years, and somehow he's got hold of this data. And he shows that it's really just a simple calculation. Like he said in chapter 2, it is very much like counting. But I think what's interesting about this is a lot of us wouldn't think to apply probability and statistics to that sort of thing, and maybe mathematicians and statisticians do that quite naturally. For some of us, we've never dared to think about it in that way. But I think that it shows just how easy it is, and that we can all do this. Essentially, he's got the data from several years. It's a counting exercise. His result is 6 over 93. The second example is he talks about a sort of logical lottery based on whether a stock on the stock market will go up and down. What's interesting about this is he actually sort of says at the end, actually this sort of probability tends to be very subjective. For example, some people might have insider information, and for them their subjective probability will be different to someone who doesn't have that information. And obviously there are rules and violations and possible jail sentences here for people trading on insider information. This then moves on to a brilliant next step, introducing Bruno Di Finetti, measuring subjective probability. I'm going to try to explain this quite concisely. Essentially, people talk about probabilities, but sometimes they might be bluffing or they haven't really thought it through. And his example is someone who comes out of a test and says to all his friends, I'm 100% sure I aced that test. I got 100%, I'm sure of it. So what's called the Di Finetti game is saying to that person, well, okay, tell you what, if you do get 100% on the test, I'll give you £1 million. Or we can play this other game with the balls in the bag, and there are 98 black balls and 2 red balls, and if you pick a black ball out of the bag, I can give you £1 million instead. So which game do you want to play? And chances are a lot of people would say, actually, I prefer to play this ball in the bags game if it's 98 against 2. But the beauty of this is that you can then adjust the number of balls in the bag. So if you say, okay, well now the number of balls in the bag is 80 black balls and 20 red balls, so which game do you want to play? Chances are he might say, actually, I do want to wait for the test result. So it reaches this sort of up-down situation where you keep adjusting the number of balls in the bag until you reach this sort of profound result. So what happened on this example is it sort of went up from 80, he preferred the test, but then it went down from 90 because he preferred the balls in the bag game, and eventually it settled at 83 black balls and 17 red balls, where he said, I'm indifferent. What's wonderful about this is Di Finetti used this with his students in Rome to guess soccer scores. So that's called the Di Finetti game, wonderfully introduced by Aczel. Chapter 6 is all about using the complements. There are some brilliant examples in this chapter, and it's a really powerful trick which he explains fantastically. It uses the fact that all events must sum to 1 in terms of probabilities. There's nothing unaccounted for. Now, to use the complement, what you do is you say 1 minus the probability of it not happening must be the result. So the probability of A or B equals 1 minus the complement, the probability of it not happening. Let's look at some examples of this. Well, the best examples are the Chevalier's dice games. So the first game was, what's the probability of 1 ace in 4 rolls of the dice? So the way to do this is to say, well, what's the probability that it's not an ace in 1 roll of the dice? Well, that's 5 over 6. So what you do is you put 5 over 6 in brackets, you take that to the power of 4, and then it's 1 minus that lot equals the answer, which is 0.5177. So this is great because you don't have to use the OR rule, and using the complement is much more efficient. The trouble with the OR rule is it's only written for two probabilities, and you can end up having to stack the OR rule. Sort of, you do the OR rule once, and then you have to do it again and again. I call it stacking the OR rule, but you really don't want to do that because it's an awful calculation, not very efficient. This way of using the complement is so much better. Look at how efficient that was. The calculation was just 5 over 6 in brackets to the power of 4, and 1 minus that lot equals the answer, and that's the probability of at least 1 ace in 4 rolls of the dice. So instead of thinking about the probability of at least 1 ace in 4 rolls of the dice, what you start doing is to think, well, what if there are no aces in 4 rolls of the dice, and you kind of use the complement. The next example is much more tricky. This is the probability of at least 1 double ace in 2 rolls, in 24 rolls of 2 dice. So in this game he's rolling 2 dice at once every time, and he rolls those 24 times, a lot of times. So what's the probability of a double ace? And that means 2 ones. Well, once again you use the complement. So he calculates the probability of it not being a double ace, and that's 35 over 36. So you put 35 over 36 in the brackets, and you take it to the power of 24. Now you do 1 minus that lot, and it equals 0.4914. An extremely efficient calculation, and brilliant when you know how to do it. So that is actually quite an interesting result. So about 49%. It's definitely not the most unlikely thing in the world. That is, that's going to happen if you play the double rolling dice game 24 times often enough. What's really interesting about this is the Chevalier calculated this wrongly and thought it was 2/3. He didn't know how to do the calculation. I think in those days, to be fair, it would have been before calculators, so we can quite easily tap it in our calculator now and get the results. But it's also about knowing how to do this, so using the complement is definitely the way to go. Look at how efficient that calculation was. 1 minus, open brackets, 35 over 36 to the power of 24. You do that and you get the result straight away. So this shows really the power of using the complement. Another really brilliant example, there's a pilot who has a 2% chance of being shot down on each mission. So what's his probability of being shot down on 50 missions? Well, you guessed it, you use the complement again. So the probability of not being shot down on 1 mission is 0.98, because there's a 2% chance of being shot down. So you put 0.98 in the brackets, you take that to the power of 50, because there are 50 missions, and then you do 1 minus that lot, and you get 0.64. So there's a 64% of him being shot down in 50 missions. It's a brilliant way of doing that, and if you didn't know how to do it, you can probably imagine some people filling pages with awful calculations. It would be a horrendous waste of time, and a dreadful calculation if you were trying to stack the OR rule 50 times in a row. So it's a brilliant example of just how powerful this idea of using the complement really is. In this chapter he introduces some other examples, but I'm going to talk about just one more, which I thought was very good. He says he's a professor, someone's a professor applying for 7 jobs, and they've reached a different stage in each of the selection processes. So some it's, there are only 3 candidates left, and for other job applications there are, say, 20 left. So what he wants to know is what's the probability that he's got job A or B or C or D or E or F or G. And once again you can use the complement for this. So what he does is 1 minus, open brackets, 5 over 6 times 5 over 6 times 19 over 20 times 19 over 20 times 2/3 times 2/3 times 2/3, close the bracket. And that equals approximately 0.8143. So about 81% likely that he's got one of the jobs. So it looks like it's sort of using the oral question. What's the probability of A or B or C or D or E or F or whatever it is? But for so many of these examples, what you really want to use is the complement. This 1 minus, and then you put the probability of it not happening in the brackets, is definitely the way to go.